Okay, so we are live. Okay. All right, so I'm noticing, I'm trying to look at this on my phone right now to see what it looks like, and I am not seeing the chat on my phone. All right, so I'm noticing, I'm trying to look at this on my phone right now to see what it looks like, and I am not seeing the chat on my phone. So I am wondering now if you guys are unable to ask me questions. That would be unfortunate. I think that's what's going on too. So, all right. Well, tell you what. I think I will just maybe go over briefly a couple of example problems real quick, and unless somebody posts me a couple of questions in Schoology or figures out how to access the chat here, then I guess there's not really going to be a whole lot happening today. But I'll go over a couple of examples. Maybe you can at least watch this afterward and get a little something out of it. So let's go ahead and do a couple of example problems, and we'll move on from there. Let me pull up my examples here. Make this a little bigger. All right, so let's say, for example, okay, so let's do an example here. This is number 6 from my problem set that I gave for homework on geometric mean. It reads like this. A man travels 9 kilometers due north. Then he goes 8 kilometers due east and 3 kilometers due south. How far is he from the starting point? Okay, so we take a look at this question. We pick some kind of a starting position. We'll say this is his start. Now from here we go 8 kilometers north. So we'll use up the page to be that. So it's going to be 9 kilometers. Then he goes 8 kilometers east. So a little shorter, and we'll use right to be east. Now east and north are at a 90-degree angle. Then it says 3 kilometers south, so that'll be shorter and be here. That's also 90 degrees. How far is he now from the starting point? So then these two connect right here. Okay, so this is what we're looking for. All right. Now, the way that this problem works is we turn this top piece into a rectangle and the bottom piece into a right triangle, like this. So when I do this, I know this piece is 3 because that piece is 3, and I know this piece is 8 because that piece is 8. Since this is 3 and the whole side is 9, therefore 9 minus 3 makes this side 6 kilometers. Well, now I have this right triangle showing right here. This is now my right triangle, and I know 2 of the sides. So, using the Pythagorean theorem, we have 6 squared plus 8 squared equals x squared. and then we solve this. I'll be back in just a minute. All right, whatever you guys are doing, do it quieter, please. I told them watch me at 10:30. It's 10:43. Okay, so still no questions here. Let's check Schoology. No questions on Schoology. All right. Let's do another example, I think. Sure. So here we have this figure. All right, and the question is segment AB is equal to, the length of segment AB is what? Okay, so this problem is a pretty interesting problem, I think, because you have to figure out the length of this full side of the triangle and this full side of the triangle. And then from that, you'll be able to calculate this, because this, AB, is our hypotenuse. So here's what we do. We pretend like this triangle is bigger, like this. Now, once it's bigger, then we can say, okay, well, this was 4. This piece here is 1, which makes now this bigger side 5. This was 7, and this was 5, which makes this bigger side 12. And then we use Pythagorean theorem again. So then 5 squared plus 12 squared equals AB squared. So we get 25 plus 144 equals AB squared. So then AB squared equals 169. So square root both sides, and AB is 13. Circle geometry problems. Yeah, we can do that. Let me find a couple here. Do you have any specific types of circle problems? Do you mean like chords and secants? Do you mean some Let's see, what else could we be talking about? Let me find my circles problem. It's a different unit for me. We're working in geometric mean and such, but I'm happy to help. Alright, so are you talking about problems like, for example, something like this? Okay, let's see, circle in the center. So like a circle here with a triangle outside of it, like this. All right, great. So, depends on what you're given as to how exactly you solve it. Are we talking about given a radius? What are you given? What do you know? So let me see. Let's say if you're given a radius. Let's say you're given this radius, and now you're going to need more information than that. Okay, so let me find a couple of example problems like it. Nope, not on this assignment. Okay, there's one. All right, so here's an example problem. Let's say this is 23 feet, and this is 15 feet here, and this is 26 feet. All right, are the okay, so let me back that up. Not are the, let's just erase this part because we don't need it. So the question is perimeter, correct? So like perimeter okay, so to get the perimeter, we're going to need to know what this missing side is here, because perimeter is going to be all of the sides added together. So for this one, we get, this is 15. So the idea here is these are all tangent lines. So since this is a tangent line, that means it's perpendicular to the radius here, perpendicular to the radius here, perpendicular to the radius here. That also tells me that these two segments here and here are congruent. So the way this works is if that's 15, then this one is also 15 right here, this little piece here. And since the whole side here is 26, 26 minus the 15 makes this side 11. Once we have that as 11, then the same logic applies here. If that's 11, then this is 11. So then 23 minus 11 makes this one 12. And if this one's 12, then that one's 12. Now we can do our perimeter by adding up all the way around. So we get perimeter equals, we can add up all the little pieces, or we can do these two big ones and the two little ones, it doesn't matter. So here we would do, let's say all the little ones, just to be consistent. 12 plus 11 plus 11 plus 15 plus 15 plus 12. So then we add that all together, and that gives us our solution. So 30 plus 24 is 54, 65, 76. Okay, so let's see, base of the triangle, length of the side. Okay, great. So the idea on these is really knowing that these two pieces are congruent. And the reason they're congruent is because it makes this little kite shape with these two radius. These two radius here makes a kite. So same, 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 and same. All right, what do you think? Does that answer your question? Got any more? You are most welcome. Well, barring any other questions, I guess I'll do a couple more just quick examples of something else. And then we'll see where we're at. Okay, so where am I? Example 3 of geometric mean. So let's say I have this. This is 10, A, C, 5, B, 3, perpendicular, D, CD perpendicular, AB, AC is 10, BC is 5, DB is 3, how long is AD? Okay. So we can use a rule directly for this if we want, and that will work great. Or we can redraw the triangles, which is the way that I actually like to do it. But gave my students the rules for these, so let's lost the problem. Where'd it go? There it is. All right, so here's what we're going to do on this problem. We're going to take the Pythagorean theorem here and solve for this missing piece. Let's just break it into parts. We'll call this an altitude. So we're going to label it A for altitude, because an altitude is a segment that goes from a vertex and then it's perpendicular to the side across from it. Right? So I just choose that letter because that's the word for it. So then altitude. So now to solve for altitude, I'm going to use Pythagorean theorem here. Since this is a right angle here, that makes this a right angle here also. So then a squared plus 3 squared equals 5 squared. Gives me this. So then my a squared, I'll subtract and get 16, which makes a equal 4. All right, so now that I have a equals 4, what I'm ultimately looking for here is this AD number right here. So then to get AD, I'm going to use Pythagorean theorem again, but with AD squared plus 4 squared equals 10 squared. So that's what I write. AD squared plus 4 squared equals 10 squared. So then we factor as best we can. So this looks like 4 times 21. So then AD is going to be square root of 4 is 2 times the square root of 21, which does not simplify. Let's do an example or two of special right triangles here. So here, let's say first, I guess let's do the rules. So there's two kinds of special right triangles. We've got our 30, 60, 90, which has these ratios. Our shortest side, let's call it 1. And then if that's 1, then this is 2, yeah, then this is 2, and this one is the square root of 3. And then we have a 45, 45, 90. And for that one, this is the 30 right here also. So this one, these are both 45s. Then we have 1, 1, and square root of 2. So those are our special right triangle rules. And then here, let's do a quick example. So we have a triangle here. So this is 60 degrees, and this is also 60 degrees. This will be 12, and this will be x. All right, so we find our other angle real quick. This is 90, this is 60, which makes this one, we figure it out by doing, well, we can know that it's always going to be a 30, 60, 90. If we recognize we have a 60 and a 90, the other one had to have been 30. But if you don't immediately recognize that, then you could say the angle question mark plus 60 plus 90 equals 180. Because triangles always add up to 180. So then angle question mark is going to be equal to 30 after that. So that's 30 degrees. Now we're going to take that triangle and we're going to organize it, or rather we're going to redraw it. Let's say that, reorient it. So this triangle right here, we're going to reorient it to be kind of in this shape, just because that's my template and I like it to look the same. So I'm going to pick this triangle up and kind of turn it sideways like this. So my 30s match up. Okay. And then I'm going to mark the numbers that I know. Well, next to the 30 we had this x and our hypotenuse was 12. Right. So now those correspond to these numbers here. So we write a proportion, 12 over x equals 2 over square root of 3. This is just like our proportional, or the proportions we wrote doing similar triangles. Right. These two triangles are similar because of angle similarity. We recognize they both have a 30, they both have a 90, so they're similar. Therefore, I can write a ratio of corresponding sides. Once you've got it, then you cross multiply. 2x equals 12 square root of 3, x equals 6 square root of 3, and we're done. Well, let's see. One more. Yeah, one more. So let's say we have, there we go, I can see now. Let's say we have a triangle like this. We have an x and we have a y, so two variables. Okay, so there it is. Now, just like I did before, I'm going to reorient this thing so that it's shaped the same way as the one above. If you can do this in your mind without having to write it down, great. If you can't, you can always write it out this way. The 30 goes here because that's what it was in our template, like our definition that I put up there. So across from the 30, right, across from the 30 should be our x. The other side that makes the 90 is y, and then our long side's 2 square root of 3. So now we have it all set up. It's a no-brainer at this point. So 1 square root of 3, 2. So just like before, we're going to make a proportion using this. We'll make one proportion for x and one for y. So here, the one for x is going to be like 2 square root of 3 over x equals 2 over 1. That'll work, right? Because that's corresponding pieces, Gives us 2x equals 2 square root of 3, x equals the square root of 3. Then for y, we'll do the same thing. 2 square root of 3 over y equals 2 over square root of 3. 2y equals 2 square root of 3 squared. Square root of 3 squared is just 3. And then when I divide by this 2, I'll end up with y equals 3. Okay, well, unless there are any more questions right now, I'm going to go ahead and end the stream, but I will hop on again tomorrow. If you've got any more questions, I will be happy to help out. For now, now. I'll give you just a minute to see if there are any more questions. You are most welcome. I hope you have a wonderful day, and I will be on again tomorrow, same time. Take care.